Welcome to this presentation on transforming 5G with open and disaggregated network architecture. My name is Ganesh Shenbagaraman, Head of Integrated Products and Ecosystem in Radisys. And in this presentation, we are going to talk about the promise and potential of 5G and how open and disaggregated network is going to suit various deployment needs and the new ecosystem that is emerging and enabling this transformation. And we'll also talk about the various deployment scenarios and the disaggregation network architecture fitting into those needs. So that's the outline of the agenda we have, and we will get into this discussion quickly. Before we talk about the 5G, a quick introduction about Radisys. We at Radisys have been pioneers in supplying protocols software stack on open interface basis for decades now under the brand name Trillium. And we have supplied stack to multiple vendors in the ecosystem from 3G days to 4G to 5G now. And we've been partnering with the ecosystem and contributing to the industry forums. And we've been part of the various open forums like Small Cell Forum, XRAN and ORAN, and TIP and ONF. Now, with that philosophy driving our productization, and we have brought out solutions with open interfaces in 4G and 5G in the RAN side, eNodeB and gNodeB solutions, small cell solutions, and we have got CPE and 5G core network solution, also the UE protocol side solutions as well. And some of the contributions which we have made to the open source contributions also is another step towards our commitment to promoting open interface-based solutions in the market. With that quick introduction, let's get into the 5G architecture and the promise and potential of 5G. Here you see a diagram which is typical of a 3GPP architecture, and with a minor change there, the RU and DU are shown as different entities. Otherwise, it's a perfect example of a 3GPP-based architecture. And what has happened in 5G is a true transformation from a standardization point of view as well. You see the 5G core network is fully cloud native now, services based, and this can enable a lot of services based on a web style architecture, and cases like end-to-end network slicing, the features of end-to-end network slicing can be used for multiple use cases and monetizing from an operator point of view. So that's one aspect of the transformation or change in the 5G network. And in the RAN side, there are quite a few things. The new radio and its different features, especially the bands, the FR1 and FR2 bands, which gives flexibility to the operators to choose appropriate bands for coverage and capacity. These are called wide bands or ultra wide bands. The amount of bandwidth that is available in these bands and the throughput it can drive is a benefit of rolling out 5G. And 5G also supports flexible numerology and beamforming aspects that gives its versatility and deployment suitability in various different scenarios of deployment. You see this architecture of the network. The 5G CN is connected to the CU and DU in case of a disaggregated RAN, and through the backhaul, the CU connects to the 5G CN through the backhaul, and the DUs are connected to the CU through the mid-haul or the F1 interface. And in case of small cell deployments, these small cells directly talk to the 5G core network. With this kind of architecture in 5G, we will be able to address the broad use case categories of enhanced mobile broadband, eMBB, driving several Gbps of throughput, and also the ultra reliable low latency communication, which is suited for some of the industrial applications and automotive applications. We also have the MMTC use case, which will be supported in 5G. This makes it possible for us to support millions of IoT devices to connect to the 5G network, both on the RAN and core network in a seamless fashion. This is the power and versatility of the 5G network as is. And if you add the approach of open RAN on top of this, the possibilities are endless. And that's what the next slide talks about in terms of the details. This is a little bit busy chart in some sense. There are so many interfaces shown, details shown here. Let's take these details one step at a time. And all the red dotted lines shown in this architecture diagram are the newly defined ORAN or the open interfaces, and which is the work being done by the ORAN Alliance. And the 3GPP interfaces are also shown in solid blue lines. And again, take a look at this architecture. The RUs are connected to the DU through the ORAN fronthaul. This is an important innovation and a step in standardization that ORAN Alliance has made significant progress. And a lot of vendors today are releasing products which are ORAN compliant, both from a DU point of view and the RU point of view. And we also see that these interfaces E2 and A1 are also defined, which allows us to use what is called the RAN intelligent controller. There are two flavors of RAN intelligent controller, the near real-time rig and the non-real-time rig. The near real-time rig hosts what is called XApps. These can be sophisticated algorithms or AML-driven apps, which have the logic and intelligence to drive the RAN in a very autonomous and intelligent way. The intelligence comes by the collection of statistics and KPIs through the E2 interface and the O1 interface. And the non-real-time rig reacts a little slowly to the changes in the network, and that typically runs the AI and ML algorithms, the artificial and machine learning algorithms. And if you look at this, the artificial intelligence and machine learning is taking all its inputs from the SMO, or the service management and orchestrator entity, which is centrally controlling all the nodes through a uniform O1 interface, and all the statistics and KPIs collected in the network are fed into the non-real-time rig to derive the appropriate algorithms by applying artificial intelligence. So this kind of closed loop architecture, you see two loops. One is an inner loop with the near real-time rig, and the other one is the outer loop with the non-real-time rig. These two rigs make it possible for the operators to optimize the network and drive them autonomously. So the advantages of Open RAN is not only the power of the new open interfaces, it makes it possible to virtualize almost all of the network with the exception of the radio. And this disaggregated architecture allows the manufacturers and the operators to pick the best in breed components. And one of the underlying concepts here is the hardware software decoupling or separation. So with the open interfaces making multi-vendor RAN possible, and the intelligence aspects coming through the rig, and the sophisticated automation orchestration that is possible, the networks are going to be a lot more self-driven with the open and disaggregated RAN solution. How does it happen in terms of the products? What are the enablers here? We will look at it in the next slide. If you look at this next slide, these are the technologies and the categories of different product lines and components which make it possible to build a completely hardware software decoupled and intelligent RAN. If you look at the picture from the left, the hardware components, the general purpose hardware from different companies, the different processors, are making it possible now to run the RAN and core network elements. In case of acceleration needed for some of the specific functionalities in RAN, you can either use an FPGA or an ASIC or GPU, and you might also use a smart NIC to accelerate some of the data path related processing. And this all makes it possible for COTS hardware, commercial off-the-shelf hardware, to be used in the hardware. And added with it, if we can bring in the cloud platforms, the general hyperscale platforms that are being used in the web technologies, the cloud platforms have become more capable, and the software infrastructure, if they are added on top of these powerful hardware components, and with the addition of a service management and orchestration entity, now we have a very, very powerful platform, which is best in class, available for the OEMs to build the ORU or the CUDU elements or the rigs. Now the OEMs can focus on their core expertise in building the appropriate RAN technologies, whether it's a radio or a CU or a DU or a RAN intelligent controller. And this is the change of the transformation with the possibility of a disaggregated RAN ecosystem. And the apps which can reside on top of these elements, especially the rigs, the artificial intelligence and machine learning algorithms, the X apps which sit on the near real-time rig, or the R apps which sit on the non-real-time rig, they make it possible for a very, very sophisticated operation possible, or a value-added product to be out in the market. With this level of disaggregation and components being brought in, integrated to build a complete RAM, there is always a need for system integration. And so this is often seen as a challenge. It need not be a challenge in our view. The system integration aspects are being addressed in forums like ORAN Alliance through specific focus on end-to-end system test cases, interoperability and integration test cases through some of these standardization activities. The test vendors are also gearing up, and some of their products are already available in the market to test those open interfaces for conformance, interoperability, functional and performance testing. So that makes it possible for us to integrate multiple vendors' RAN components into one solution without much pain. And thirdly, and the most important aspect, is the expertise being brought in by a system integrator who is specialized in RAN. We need a system integrator who is specialized in integration of the RAN nodes and making the RAN functional integration and network deployment readiness. That's one of the key things, expertise areas, which is needed to make sure that a multi-vendor RAN is not only interoperable and functional, it is going to perform and meet the benchmarks of anyone who is deploying the network, either it's an operator or a private network. Right? So how does it all fall in place for different deployment scenarios? Let's look at that in the next slide. You might have different flavors of deployment. It could be an indoor deployment to start with. It could be serviced by a small cell or a DU. It could be an FR1 spectrum or FR2 spectrum based on the coverage and capacity needs inside the building. So you might service it with a small cell or an indoor DU. And again, a disaggregated RAN architecture will help you do that. And there are technologies available here as well. There are companies making it possible through the small cells platform on which the software stacks can be ported and integrated. And such solutions are available to have small cells or DU for indoor solutions for their coverage and capacity needs. It could be private networks, it could be industrial needs or enterprise or healthcare, any such use case. Such private networks can be enabled by adopting appropriate spectrum strategy, either a dedicated spectrum, licensed or unlicensed, or a shared spectrum, or it could be through a network slice. All these combinations and possibilities are available in 5G. So the standards support all of these things, and the products here as well, a combination of DU and CU and RU to cater to the specific needs of such industrial or private network deployments, right from the bands to the components and the management needs, can all be enabled through a disaggregated RAN architecture. And the other possibility could be the outdoor coverage in scenarios like a stadium coverage, where there is a tremendous expectation on the uplink or the upstream traffic as well, where the users can upload videos and stream something. So 5G as a technology base offers the possibility of flexibly configuring uplink and downlink throughput to give more on the uplink as per need, and we can deploy a small cell or DUs, a bunch of small cells or a bunch of DUs to cater to the need, the temporary need or the occasional need of a stadium kind of use case. Where we could see a significant uplink traffic, and that can be catered by configuring the network appropriately. So disaggregated architecture again will come handy to service these use cases. And lastly, the most important and mainstream use case of an operator network, where this is typically called a macro network of an operator. We can deploy the completely disaggregated network there with all the CUs and DUs and RUs spread out, different band combinations, FR1 and FR2, with the availability of rigs, both the near real-time rig and the rig on the non-real-time side and the 5G CN, to cater to different use cases and services which can be enabled by the operators. This can be a very, very rich and versatile ecosystem, and the disaggregation network is the right way to deploy 5G and derive the maximum benefit out of these possibilities. So we see, in summary, we see all of these use cases can be easily addressed by adopting an open RAN and a disaggregated RAN approach towards deploying 5G. And we strongly believe this is the future of 5G, and that's how 5G will evolve into 6G. And we are encouraged by the increasing adoption in the market for the disaggregated architecture. Hope you find this presentation useful for you. Thanks for listening in.